Here we go. So we graphed the parent function of a cube root. So before break, a couple weeks ago, we did the parent function of a square root, right? And we had a restriction involved because when I wanted you to take square roots of negative numbers, we got into the i's, right? And you can't graph that. But if I want you to do the cube root of negative 27, can you do that? Yes, you can. What is the cube root of negative 27? Negative 3. What's the cube root of negative 8? Josh, what's the cube root of negative 1? Thank you. Dion, what's the cube root of 0? 0. Connor, what's the cube root of 1? 1. Thomas, what's the cube root of 8? 2. Rowan, what's the cube root of 27? 3. Beautiful. So we can go all directions. We can go positive, we can go negative. Okay? No restrictions with the cube root. When we graph, negative 27, down 3, negative 8, down 2, negative 1, negative 1, 0, 0, 1, 1, 8, 2, 27. That's 26. Yep, thank you. There we go. Okay, so our square root kind of gave us like a pot of gold and a rainbow shape. We had a vertex and we did a curve from it. This time, we have a middle point, and it is semi-reflective on both sides, okay? It's reflective across the origin. Remember, that means if I take this and I switched it upside down, it would be the exact same thing, okay? So it makes like a elongated S shape, going both directions forever and ever. So what does that mean that your domain and range will always be for these functions? All real numbers. Okay. That was different for square roots because they couldn't go past that vertex or pot of gold. So your domain and range had to start somewhere and then go. Here we go forever all directions. Square roots started at a vertex and then continue to go up forever or continue to go down forever. Cube roots, if I go from left to right, is it always increasing or always decreasing? This one will always be increasing, yeah. What would make it always decrease? What transformation could happen to it to make it decrease the whole time? If it was reflected across the y or even across the x. Any kind of reflection would make it start taller and then decrease on its way down. Yeah? Go with our parent function? Yes, I think these are easier than square roots because there's no restrictions. So it's nice. Your domain and range will always be all real numbers. Okay? It'll always be increasing, or if a reflection happens, it'll always be decreasing. Okay? So let's remember some transformations. Here we have the cube root of x minus 5. Wants us to determine when the function is positive, negative, increasing, or decreasing, and then describe the end behavior of our function. Okay? Couple of ways to go about this. Yes, you can type it in, go to your table, plot some points, make the graph, and go from there like we've been doing. Or we can make our math make sense. What transformation happened with the x minus 5 under my cube root? It went to the right 5. So is that going to alter our x values or our y values? Our x values, they're going to go up by 5, right? So instead of 0, 0 being the middle, now it's going to be 5, 0. Right? It physically moved over to the right 5 units. So your y values, we can go ahead and copy those down because those weren't affected. What was affected was our x values, and they're going to increase by 5. So see how this went from 0, 0 to 5, 0? So instead of negative 27, it's going to be negative 22. Instead of negative 8, we're going to have negative 3. Instead of negative 1, we're going to have positive 4. Good. I'm going to graph these real quick. Negative 2, negative 3, negative 3, negative 2, 4, and negative 1. All right. What's my next x value going to be after 5? A 6. Then what? 13. And then 30, almost 32, which actually doesn't fit. So our shape is still there, but the whole thing did get shifted over to the right 5 units. Okay. So when you understand your transformations, that actually helps your math be quicker, right? Instead of typing it in, looking at your table, where you know there's going to be a whole bunch of decimals in between negative 22 and negative 3, right? If you know what you're doing, you can make it quicker. All right, positive versus negative. Let's remember what this means, because it's been a hot minute. Positive versus negative means positive y values and negative y values, okay? What x's give you a positive y? What x's give you a negative y, okay? And so it depends on where we're going to cross over our x-axis. What is our x-intercept going to be? It's now a 5, yeah. So where are my y's a positive? Well, that's when my x's are greater than 5, right? Remember, your arrow actually points to the right of 5 is where I have positive y values. So when x's are greater than 5. What x's will give us negative y values? Well, that's the x's on the left side. So my x's that are less than the x-intercept of 5. Is this entire cube root increasing or decreasing? Increasing. There is no decreasing interval because there wasn't a reflection. We talked about that. So we're still increasing the whole time. How do I say the whole thing is increasing? All right. Yeah, we can do negative infinity to positive infinity. What's another way we could say all the things? We could do that double-lined R from before, all real numbers. You can write out the words, all real numbers. They are all representing the same thing. Our end behavior. Okay, so when my x's go negative, so on the left-hand side, what is my function doing? Is it increasing or decreasing? It's decreasing. So how do I say that with fancy symbols? Negative infinity. Good. How about on the right side? As x's get bigger, what's my function doing? Going up or going down? Up. That's increasing, so we're going to positive infinity. Your end behavior and your increasing, decreasing will always be the same unless a reflection happens. And if it's reflected, it just gets switched. Everything flip-flops. Think you're ready to do one? I think you are. You try the next one. You're going to graph f of x equals 4 times the cube root of x. You're going to determine again when it's positive, negative, increasing, or decreasing. Then describe the end behavior. Okay. Can we help you get started? What transformation is happening with 4 times the cube root of x? You're multiplying by 4 on the outside. If it was inside, yes, but it's on the outside. So what's it doing since it's on the outside? It's a vertical stretch. Vertical stretch by 4. So is that going to affect my x values, or my y values, or both? It'll only affect my y values. It's a vertical stretch, right? What's vertical? Your y's, right? So are your x values going to change from your parent function? No. Your x's this time stay the same. Your y values are what's going to be changed. Okay? So your x's are still these guys. This is where I'm going to stop. Your y values this time are what's being altered because it's a vertical stretch by 4. All right, check with me. Make sure our table and our graph is matching. How'd we do? Good. All right, so positive versus negative, looking at above or below that x-axis, where are we going to have positive y values? When my x's are what? When my x's are greater than 0. Good. And so where are we going to have negative y values? When x's are less than 0. Beautiful. Is my entire function increasing or decreasing? Increasing. So we're going to say all real numbers. Nothing is decreasing. And my end behavior should be the same as last time because there was no reflection. So that bottom part's not going to change unless we reflect. We do okay? All right. Yes, ma'am. As I move to the left, my function's going down. Mm-hmm. All right, moving on to the back. Example 2. What do you notice about number 2? Yeah, I gave you values in your table. Okay, so this time we're going to do negative cube root of x plus 2, and we're going to pair it to the parent function of the cube root of 2. Okay. When there's more than one function going on, it's nice to give you a piece of it, or you could just use your calculators like in the next one. But here I gave you x values. You can type in your function, find your table, complete it that way, or you can plug values in. Okay, it's totally up to you. If you were to plug in negative 10, what is negative 10 plus 2? What's the cube root of negative 8? Negative 2. What's negative 2? Positive 2. What's negative 3 plus 2? Almost. Negative 1. It's okay. What's the cube root of negative 1? And what's negative 1? Positive 1. You were just giving me the answer. You were ahead of us. Negative 2 plus 2, 0. Cube root of 0 is 0. Negative 0 is still just 0. Negative 1 plus 2, positive 1. Cube root of 1, 1. And then there's a negative out front. 6 plus 2 is 8. Cube root of 8 is 2 with the negative out front. Okay. So when we plot these points in a minute, what should we expect to see? What transformations happened this time? There you go. So we have a shift to the left 2, and it's going to reflect over the x-axis. So we're finally going to see what that's going to look like for us. So it should start up and then go down, right? That's what we should kind of picture in our head with that reflection. Here we go. Negative 10, positive 2. Negative 3, positive 1. Negative 2, 0. Negative 1, negative 1. And then 6, negative 2. And that is what we get. Bless you. Good. So example 2, I gave you some values. Example 3, I gave you nothing. Okay, I don't even give you a table. With example 3, we have 2 times the cube root of x minus 3 plus 4. Describe the transformations from the graph of, that should be cube root of x, to the graph of g. So, what's happening here? What transformations can we expect to see? What's that 2 out front? Good. A vertical stretch by 2. And then what's the x minus 3? Right 3. Thank you. And then what's that plus 4 doing? Up 4. All right, so I'm going to picture in my head that middle point should go left 3, up 4, and then it's stretched, so it should be like a long, it should be stretched up and down a little bit more, elongated S. So let's make sure it makes sense. This one I would type into your calculator, handheld or Desmos. I'll show Desmos up here. If there's something in there, just cancel it out. If you don't know how to get to the cube root button on your handheld, you'll push the math button, and then your option 4 is your cube root. Okay? If you're using Desmos, you're going to push the functions button right here, and it's all the way at the bottom. Cube root of x minus 3. Move your arrow out and then do plus 4. Desmos, you know you can pinch in and out for zooming. And there are some points that they've given us. There's a couple of them. Remember to make your table. You can push the little wheel for Desmos and change that to a table, and they do give me points. Okay, so -5 was on there. There we go. We know -5, 0. Looks like 2, 2 was a nice point. Come on. Whatever, that's fine. 2, 2 is a nice point. With your handhelds, you can just keep scrolling. Desmos, you have to type in numbers. So if I type in 3, oh, that's nice. Okay, so 3 works. 4 works. 5 does not. That's okay. I'll just erase it and put a 6. Nope. 7, 8, 9, 10, 11. Oop. 11 works. Okay. So handhelds, it's harder to zoom in and out, but your table is already there for you completely. Desmos, it's easier to zoom in and out, but the table is a little bit more involved. So it really is just what your preference is. Or heck, maybe you could do both. All right, so let's graph some of these points. So we saw that -5, 0 was a good one. 2, 2 worked. 3, 4, 4, 6, and then 11, 8. There we go. Our middle piece did get moved to the 0.34. That makes sense. And it's taller now, so it got stretched. I don't know if you noticed this pattern, but up in, like here, see how the other points are just 1 away from the middle on each side? That happened on the front. Here, each point was 1 away. Each point was 1 away, unless there's a stretch going on, right? Look at this stretch. They were 4 away from both sides. Was it my stretch of 4? It went up 4 over 1. This had a vertical stretch of 2. See how they went up 2 over 1? So that's a nice little pattern you could notice from your stretches. All right. Almost there. 2 more. Example 4, I've given you a table that shows 2 functions in the same table. Okay, so the table approximates 2 cube root functions, f and g. Describe the transformation from the graph of f to the graph of g. Okay, so what's happening? Talk to your neighbor. Some of you might be sitting with somebody new, so you can introduce yourself. Okay, talk about what you see in the table. Ready, set, go. How does f relate to g? So yes, we noticed that it got moved to a translation 1 unit to the right of f. Good. If you were to write this as a rule, you could say g of x. How do I say to the right? We do an x minus 1 in the parentheses, right? So that's how you would write a rule. It didn't ask you for that, but I'm showing it to you. All right, last one. Ready for my elephants? Yay! Here we go, modeling real life. The shoulder height h in centimeters of a male Asian elephant can be modeled by the function h equals 62.5 times the cube root of t plus 75.8, where t is the age in years of the elephant. Use a graphing calculator to graph the function, and then we're going to estimate the age of the elephant, whose height is 200 centimeters, and whose height is 175 centimeters, okay? If it was algebra, I could just make the equation equal to that and solve. We haven't done that yet. It's tomorrow. I'll show you the algebra way tomorrow. Today is the graph way, okay? So what we're going to do is we're actually going to graph two different things in our calculators. So whether you have Desmos or handheld, you're going to enter two things in. In your first spot, so my handheld, you have a Y1, Y2. Desmos, you just have two different slots, okay? In your first slot, you're going to put in the function 62.5 times the cube root, we type in x, plus 75.8. And then your second entry for this one is going to be 200. Okay, so my handhelds, you have two different pieces you're going to type in. And I'm going to pull up Desmos here. For Desmos, here we go. I'm going to get rid of this. Here we go. 62.5 times the cube root of x, and then plus 75.8. And then in your second line, for my Desmos people, you have to actually type in y equals. Because Desmos can do y, they can do horizontal and vertical lines in Desmos, so you have to actually type in the y equals. My this is blocking you. There you go. Okay. You probably can't see it, and that's because we need more y's, right? We just said that y equals 200, so I'm going to need that to happen. My handhelds up on the board, you're going to push your window button and change your y max to be about 300, okay? Something more than 200, right? My Desmos friends, you know you can zoom out until you see both things happening, and there it is. Okay. We want to find the intersection. Where do these two functions meet up? Where are they equal to each other? So Desmos, you can just tap that, and we see it's 7.847, right? My handhelds, look at the board, the blue. You can calculate the intersection. You'll push your second button and then trace. Go down to the intersect option, push enter. And then when you see your graph, push enter 3 more times. And make sure you get the same intersecting point. So about 7.847. .847, comma 200. So that was the intersect. So my elephant is about how old? Elephant is about 8 years old. All right. Does that make sense how we did that? Okay, so this was our intersecting point, because you want to know when they equal each other. So we have age, and then we have height. So if you're good with that, I want you to try the next one. And if you're having calculator issues, I'm going to walk around and come help you. Okay, so you're trying to find how old is an elephant who has a shoulder height of 175 centimeters. Okay. So the only thing you're changing this time is instead of 200, you should plug in 175. All right, I'm going to pause and walk around. Yep, your intersect was about 3.998. So your elephant this time was about 4 years old.
So then for you, 3.998 would still be the day before.
All right. We good? Beautiful. Good job today.